So, hello everyone. Today we will start the next lecture of module 7, coating of calcium phosphate on titanium surface. So, basically here we will just see one example of physical coating of calcium phosphate. So, we will just see how the calcium phosphate is coated on titanium using the physical method. So, in the last lecture we discussed what are the different surface modification route. So, this included the physical modification, chemical modification and as well as the biological modification. So, there we discussed in the physical modification what are the different methods, including the plasma spraying, laser cladding, the RF sputtering. In the biological route we discussed how the biological macromolecule can be immobilized or applied on the surface, and in the chemical modification route we discussed that chemical vapor deposition, formation of self assembled monolayers, coating of polymers, particularly the grafting to and the grafting from. So, in today's lecture we will just see one example from this physical modification technique, particularly this laser cladding and RF sputtering. I will just see how we can coat the calcium phosphate on titanium surface. So, we will compare if you coat the calcium phosphate and titanium using different methods, what will be the properties or what will be the features of the modified surfaces. So, calcium phosphate, as the name suggests, it will have calcium as well as the phosphate, and this calcium phosphate is the main mineral component of the human bone and the teeth, and it is highly biocompatible inorganic biomaterial. It has the biosimilarity. It has the biosimilarity. So, this calcium phosphate can be this monocalcium phosphate, dicalcium phosphate, tricalcium phosphate or hydroxycalcium phosphate. So, basically the hydroxyapatite, that is a hydroxycalcium phosphate. So, this is very much biosimilar to the bone. It has a hexagonal structure and its Ca by P ratio, calcium and phosphate ratio is 1.67, that is very close to that of the bone. So, that is why this calcium hydroxyapatite, or you can only say hydroxyapatite, is mostly preferred by ceramic for the bone tissue engineering or orthopedic applications. Now, apart from that, other phase is the tricalcium phosphate, that is also a common phase, tricalcium phosphate. It is stable at the room temperature, and TCP is commonly used for the bone graft substitute, but its rate of degradation is much faster than the hydroxyapatite. And during the synthesis of calcium phosphate, mostly TCP is present with the hydroxyapatite. It means a mixture of hydroxyapatite and beta TCP is formed, and this is referred as biphasic calcium phosphate or BCP, and which is also used for the bone replacement. So, here we will see we will try to apply the physical methods or physical coating of, particularly we are more interested in hydroxyapatite on the titanium surface. So, why to titanium? Because titanium is already being applied for the bone tissue engineering, especially for the bone implant, for the dental implant. So, to improve its biocompatibility or bioactivity, hydroxyapatite can be coated, because hydroxyapatite biodegradable material, bioactive material, biocompatible, and it has the similarity with the bone. So, this is your substrate. Substrate means your titanium, then this is your target, target means this is your HA hydroxyapatite. So, we have to first prepare the target. So, for preparing the target we can form a pellet, and the pellet we have to keep inside that sputtering chamber. So, here the method was applied RF magnetron sputtering. So, this is your target and this is your substrate. Now, distance between the target and substrate was about 5 centimeter. Distance is about 5 centimeter, and for the plasma creation the inert gas, here the argon was used and RF power was 30 watt. 30 watt RF power was used. So, in vacuum pressure was maintained is 3 into 10 to the power minus 2 millibar. So, once we apply the RF pressure, as you remember when we discussed the working principle of the RF sputtering. So, the inert gas will form the plasma, and that plasma will act on the target, and target will be part of the plasma and it will get deposited on the substrate. So, deposition time we vary it as 4 hours, 6 hours and 8 hours. Now, as we discussed, if you vary the deposition time means we are giving more time for the deposition. So, typically this thickness increases, it may be linear, it may be exponential, it depends on the what is the power and what is the coating material. So, here we observed that with increase in the deposition time the coating thickness was increased as expected. So, it was 400 nanometer at 4 hours, at 700 nanometer at 6 hours, and at 8 hours we got about 1100 nanometer thickness. Now, apart from the thickness, although our target was HA, we started target was HA, but during the deposition as we discussed, the stability is a concern because due to the temperature. So, here along with the HA, the beta TCP phase was also formed, that is why we call it a biphasic calcium phosphate, and here this deposited film was analyzed by the XRD. So, this surface characterization part we will discuss in the next lecture. It was analyzed by XRD, we found that it has the HA hydroxyapatite as well as the beta TCP phase. So, this says that although we started with the pure hydroxyapatite, but during deposition, particularly these physical methods, because of the effect of its working and temperature, we end up with the mixed phase rather than the pure phase. Now, after measuring the thickness, we analyze its physical property, particularly roughness and the contact angle. So, surface roughness was also found to increase with coating thickness. So, you just see with increase in the coating thickness, the surface roughness was increased, but still the roughness was in the nanometer range. Now, similarly, if you are depositing the hydroxyapatite, so hydroxyapatite is expected to be more hydrophilic as compared to the titania. So, for titania the contact angle was close to 89 or less than 90 degree, and after the deposition, depending on the thickness, we observed that the contact angle was, or you can say the contact angle or wettability decrease. Here for the contact angle measurement we used SPF, that is the simulated body fluid, to measure the contact angle. So, here you can say it is having on the titania, it is having very close to the 90 or 89, 88. Here contact angle is decreasing, further decreasing, and the again decreasing at the highest coated or surface, highest thickness surface. So, what it says is with increase the film thickness, surface roughness is also increasing, and because of the surface roughness as well as the material property, because if you see here, because of the hydroxyapatite there is a decrease in the contact angle, but again with the increase in the roughness, again there is a further decrease in the contact angle. So, it says both material chemistry as well as the roughness are playing a role in the surface wettability. Now, we try to relate that the surface roughness with the wettability, and we found that it follows the it agreed to the Benzal equation, which says that contact angle on a rough surface is RF is the roughness factor into the true contact angle. So, what it says, if the theta is less than 90 degree, so contact angle decreases with increase in the surface roughness. That is what we observed in the last slide, that RA was increasing and at the same time the contact angle theta was also decreasing with increase in the RA. So, it says it follows the, it agrees to the Benzal equation. Now, this was the case of the RF sputtering. Now, we will just see if you are coating the same thing using a different method, that is the laser cladding. So, here we are going to apply the laser cladding for the coating of hydroxyapatite, and along with hydroxyapatite we also coated the mixture of titania and hydroxyapatite. Titania is used because titania is expected to be more hydrophilic, plus as we are coating on the titania, and if you also coat the titania, it expected to improve the adhesion strength between the coating and the substrate. So, here in case of laser cladding, the precursor was hydroxyapatite 100%, and in case of mixture we had different ratio of the titania and hydroxyapatite. So, here you just see we had 500 micrometer thick layer of 100% hydroxyapatite, and in case of mixture we had the 5 different layers, that is what we are calling the graded material. So, initially first layer was 100% TiO2, then 25% HA, 75% TiO2, then 50% HA, 50% TiO2, 75% HA, 25% TiO2, and then 100% HA. These are the 5 layers. So, total thickness in both the cases was same, and this is how it works. You have a argon gas, this is a laser beam, and this is your substrate. So, if you just see here, this titanium substrate, this is the prepared powder of the thickness of the 500 micrometer, and once we clad apply the laser, so basically it melts and gets deposited on the surface. So, here you see this is the cladded layer, this is the pre-placed powder, and here we are applying the laser beam. So, for the pulse laser we use this neodymium doped yttrium aluminum garnet was used for the pulse laser, and laser power and wavelength was 500 watt and 1.064 micrometer was the wavelength. Laser density was 21.6 joule per millimeter square. We applied the inert gas argon at the pressure of 0.2 megapascal, and scanning speed was 4 millimeter per second. So, after this laser cladding, let us see the surface properties of the coated titania. So, here uncoated the contact angle was close to 90, but after 100% HA the contact angle is 70. Further, when we mixed it with the titania and HA, as expected the contact angle has further decreased, it become more hydrophilic. And again if you just see here the roughness, the non-cladded titania roughness was close to 1 micrometer. The functionally graded material has about 3.5 micrometer roughness, and hydroxyapatite cladding was at the highest roughness of 5. So, what it says is, as compared to the RF sputtering, the roughness RA is higher. This is coming because of the coating technique. RA is higher as RF sputtering. So, this is again the effect of which method you are applying, because the laser has applied the high power, it melted your target material as well as the substrate and it get deposited, but at the same time it ended up with more rough surface as compared to the sputtering. Now, we analyze the adsorption of the protein, because if you remember for biointerfacial aspect we have to see the two aspects. First is the protein surface interaction, and second is the cell surface interaction. So, in the protein surface interaction we used 10% FBS and adsorption was carried at room temperature for 2 hours. So, here the adsorb amount on the uncoated surface which has a roughness of 1 micrometer. So, with increase after the coating hydroxyapatite, it has about 3 microgram per centimeter square of the adsorbed protein, and this mixture or the mixture of hydroxyapatite and titania resulted in the highest amount of adsorbed protein. So, here again if you are increasing the roughness, so as compared to this and this, the coated surface have the higher adsorb amount due to the increase in the surface roughness as well as due to change in the surface chemistry. Again in the protein adsorption what we are seeing is the effect of roughness as well as the surface chemistry. Roughness and surface chemistry both are playing the important role here. After the coating, the protein adsorption was the enhanced, and this enhanced adsorption is attributed to the surface composition as well as the surface roughness. Now, again we analyze the cell surface interaction. So, this cell surface interaction we use the human osteoblast MG63 cell lines. They were cultured in the cell culture medium at 37 degree centigrade in 5% CO2 in a humidifying chamber for 12 hours, and after the 12 hours we analyze the cell features using the microscopic technique, particularly fluorescence microscopy. So, here we just see these are the cells. So, here we stain the actin filament, we also stain the nuclei, and if you merge them, so you can just see nuclei is surrounded by the actin filament. So, if you remember the cell surface interactions, so how we experimentally analyze the cell surface interaction is in terms of percentage cell adhered, in terms of average cell area, also we just see the what is the nuclei size and circularity. So, here if you just see, we observe the maximum cell adhesion on the FGM, the coated surface, where we observe the highest edge of protein. So, what it says is after the coating or deposition of the calcium phosphate, we also observed enhance in the protein adsorption, as well as here we are observing the increase in the cell adhesion as well. Similarly, the cell area is also increasing, it means cells are also growing better on the coated surface as compared to the uncoated surface. Now, if you just see the nuclei is again, as the cells are growing, the size of nuclei is also growing on the coated surface, and as you see the cell circularity is decreasing. The decrease in the cell circularity means more proliferation, more growth. Cell circularity higher means it is circle, if it is decreasing means the cells are spreading, cells are the growing. So, what we have observed is after the simply coating hydroxyapatite based materials or calcium phosphate on the titania, it is improving its both cell surface as well as the protein surface interactions. Now, next method what we have tried, let us coat the biphasic calcium phosphate and titania on a titanium substrate, again using the RF sputtering, because in the last one we coated the calcium phosphate and titanium mixture using the sputtering. Now, here we are coating mixture of calcium phosphate and titania using RF sputtering. So, three different compositions such as 100% BCP, 25% TiO2, 75% BCP and 50% TiO2, 50% BCP film were fabricated. So, here the method we are applying is RF magnetron sputtering. So, the same as we discussed in the first case, the sputtering power was here 40 watt and we coated for 7 hours, and after the coating the sputtered sample were also annealed at 700 degree centigrade for 2 hours. So, here again as compared to the laser cladding, the roughness was lesser. For 100% BCP, the roughness was again in nanometer, 540 nanometer, it was the highest. For 25% TiO2, again the roughness is increasing to 918, and for the 50-50 mixture TiO2 and BCP was the highest surface roughness was observed 1320, 1.3 micrometer. So, this is the coating thickness of the mixture of BCP and TiO2 on a titanium surface. So, here if we just see the contact angle, this is for the unsputtered titanium surface, and after the sputtering you just see this 100% BCP biphasic calcium phosphate. This is the mixture of 25% TiO2, 75% BCP, and this is the 50% TiO2, 50% BCP. So, if you are adding more and more TiO2, it improving the hydrophilicity, means contact angle is decreasing. Also here if you just see, if you are increasing the surface roughness, again hydrophilicity or contact angle is decreasing, it means it is again agreeing to the Benzal equation. So, here what phases we had? We had the BCP means HA, TCP. So, what phases we have here is the HA, TCP and TiO2. So, now protein adsorption. So, depending on the mixture, or you can say depending on the ratio of TiO2 and BCP, we are observing the highest adsorption for the 100% BCP, then this is for the 25% TiO2 and 75% BCP is decreasing, then for the 50% TiO2, 50% BCP further decreasing. It means here the protein adsorption is following the same trend as the hydrophobicity. It means this was the highest hydrophobicity, followed by this, then in the similar manner the protein adsorption was found to increase with the hydrophobicity. Again we have analyzed the roughness factor. So, what is happening? The roughness factor was the, we have already measured the surface roughness, we have also calculated the roughness factor is defined as RF. I will just revise the RF is the actual area divided by the projected area. So, because of the roughness, the actual area is always higher than the projected area. So, this RF value is higher than 1, and with increase in the surface roughness, we are observing a decrease in the protein adsorption. So, what it says is the protein adsorption is not following the trend as expected because of the increase in the surface area. It means if you are increasing the surface area, means there should be more contact area between the protein and surface, then there should be more adsorption, but we are getting the opposite trend. So, what it says is the hydrophobicity played a major role during the protein adsorption rather than surface roughness here. So, this hydrophobicity and the composition of the film played a key role here in the protein adsorption. If you just see the cell adhesion, again it was analyzed in terms of percentage adhered cells, cell area, nucleus size and the circularity. And if you see, this is the uncoated surface, the percentage cell adhered, you coated the BCP, cell adhesion increased, further with 25% TiO2, 75% BCP, it further increased. Again we got the highest in case of 50% TiO2 and 50% BCP. Similarly, we just see the trend of cell area, average cell area, it is again increasing, then further increasing and further in. So, what it says here again, due to the coating of hydroxyapatite, TCP and titania on the surface, it has improved both. Here we observed improve in the protein adsorption, again the cell adhesion or cell surface interaction is also improved. So, here also we have used the MG63 cell for the cell surface interactions. So, apart from this, we also see the nucleus area. So, nucleus area is again it is increasing with coating 100% BCP, then 25% TiO2, 75% BCP and 50% TiO2, 50% BCP. It is again increasing, and as expected the cell circularity should decrease. So, cell circularity is decreased on the coated surfaces. So, in this way what it says is we can improve the biocompatibility or the bioactivity of the titania based implant material by simply coating the calcium phosphate. So, we discussed coating using the RF sputtering. So, in the RF sputtering, when we coated the HA, it ended up with BCP. It means it has both HA phase and TCP phase. And when we coated this using the laser cladding, because of the increase it has more phases, it has the calcium titanate, apart from that it will have the BCP and of course, this titania phase will also be present, because when in the laser cladding we also use the mixture of HA and the titania. So, particularly what happen in case of laser, we apply very high power, so that your powder or coating is melted and get deposited. So, in that case the upper layer of your surface is also partly melted. So, it also ended up with more roughness in case of laser cladding as compared to the RF sputtering, and in either way when we deposited the calcium phosphates on the titanium surface, it improved its biointerfacial interactions, its wettability, its cell surface interaction and the protein surface interactions. Further, if you want to improve its hydrophilicity, along with hydroxyapatite we can add the titanium oxide for the deposition, and we observed the highest amount of cell adhered on the 50% BCP and 50% titania coated surfaces. So, this lecture included the one example of the physical coating, particularly these two RF sputtering and the laser cladding. Substrate was chosen as the titania, which is very much biomedically relevant for bone implant and dental implant surface, and we chosen the hydroxyapatite because it has the similarity with the bone with the Ca by P ratio of 1.67. But the issue is when we are depositing with the physical methods, we are ending up with mixed phase apart from the pure phase, and the mixed phase is not having the same Ca by P ratio. Like for beta TCP, Ca by P ratio is 1.5, and also the beta TCP is more biodegradable, rapidly degradable as compared to the HCP, but we cannot control it in the physical methods, because when we apply a particular power, the material has to melt and then get into the plasma and get deposited on the substrate. In that case, because of the high temperature, we are ending up with the formation of mixed phases on the surfaces. Thank you.